Multi-protocol label switching, or MPLS, was developed to improve the efficiency and flexibility of traffic transport across large networks. While IP forwarding already works well, MPLS adds a label-based forwarding mechanism that enables scalable traffic engineering, service separation, and VPN delivery in provider environments. The value of MPLS is not that it replaces IP entirely. Rather, it works alongside IP. The control plane still uses IP routing information, but the forwarding plane can use short labels to move traffic across the provider core. This separation helps support services cleanly and at scale. A common service provider example is carrying many customer VPNs across one shared backbone without exposing customer routing directly in the core. MPLS becomes the transport mechanism that makes such services practical. To understand that, we first need to see how label switching differs from ordinary IP forwarding. In ordinary IP forwarding, each router examines the destination IP address and performs a route lookup, typically using longest prefix match. In MPLS, a router in the labeled path can forward based on a label attached to the packet rather than reevaluating the full destination IP address at every step. When a packet enters the MPLS domain, an ingress router may push one or more labels onto it. Transit routers examine the top label, swap it with a new label based on their forwarding information, and send the packet onward. At the edge, an egress router removes the label and continues forwarding appropriately. This model simplifies forwarding behavior inside the MPLS core and provides a foundation for services such as Layer 3 VPNs and Layer 2 VPNs. To make this more intuitive, let us look at the basic label switching path. A label-switched path, or LSP, is the sequence of routers through which labeled traffic travels in an MPLS network. The ingress router classifies the traffic and applies a label. Transit routers switch the packet based on label information. The egress router removes the label and forwards the packet toward the final destination. Think of this as similar to entering a controlled transport system. At the entry point, the packet is given an identifier that determines how it should move through the network core. Inside that core, forwarding is based on the identifier rather than repeated deep analysis of the packet's original destination. Operationally, this allows the provider backbone to carry traffic efficiently while supporting layered services on top. But for labels to be useful, routers must learn which labels to use. That is where LDP comes in. Label Distribution Protocol, or LDP, is one mechanism used by routers to exchange label bindings for IP prefixes. In simplified terms, routers tell one another, for this prefix, use this label when sending traffic toward me. These label bindings allow MPLS forwarding entries to be built across the network. LDP typically works alongside an underlying IGP such as OSPF or ISIS. The IGP provides basic IP reachability through the network, and LDP distributes the labels associated with those reachable prefixes. Together, they allow labeled forwarding across the MPLS domain. It is important to remember that MPLS still depends on a healthy routed network underneath. If the IGP is unstable or the core lacks IP reachability, label-based services will also be affected. That leads us to an important question. What prerequisites must exist before VPN services can be built successfully? Before deploying VPN services, the provider network needs a stable underlay. Core interfaces must be operational, IGP reachability must be correct, and MPLS transport must be functioning if the service model depends on labels. In addition, edge devices must be able to maintain the control plane relationships required for service exchange. Service separation also depends on the correct use of logical constructs. For Layer 3 VPNs, this often includes separate routing instances or VRFs so customer routes remain distinct even when customers use overlapping IP address space. For Layer 2 services, the network must correctly identify and transport frames or pseudo-wires between endpoints. A useful rule is this: do not troubleshoot the service layer before validating the transport layer. If the underlay is broken, the overlay will not behave correctly. Once the prerequisites are clear, we can compare the two major service models introduced in this course, Layer 2 VPN and Layer 3 VPN. A Layer 2 VPN extends Layer 2 connectivity across a provider network. To the customer, it can appear as though distant sites share a common Ethernet-like service, even though the provider is transporting that traffic across an MPLS or routed backbone. The provider carries frames while largely preserving the customer's Layer 3 independence. A Layer 3 VPN, by contrast, provides routed IP connectivity managed through provider participation in customer route exchange. Customer routes are kept in separate VRFs, and the provider edge router becomes part of the Layer 3 service model. This allows scalable routed connectivity without merging all customers into one shared routing table. A simple example helps. If a customer wants to connect two sites and keep their own routers handling all Layer 3 decisions, a Layer 2 VPN may be appropriate. If the customer wants the provider to participate in routing between sites as a managed service, a Layer 3 VPN may be more suitable. Both models are valuable, but they solve different problems. We conclude the course by bringing the full journey together. In this course, we began with the fundamentals of network communication, layered models, encapsulation, packet flow, and the distinct roles of hosts, switches, and routers. We then examined service router architecture, including the separation of control plane and data plane, the importance of hardware design, redundancy, and discipline verification. From there, we built a practical understanding of IPv4 addressing, subnetting, forwarding, ARP, and ICMP. We expanded into routing protocols, comparing static and dynamic routing, exploring distance vector and link state concepts, and introducing OSPF and BGP as key tools for scalable reachability and policy. Finally, we introduced MPLS and VPN services, showing how label switching supports scalable transport and how Layer 2 and Layer 3 VPNs provide distinct service models over a common backbone. The unifying theme throughout the course is that networks operate through structured layers, deliberate control plane learning, and efficient data plane forwarding. As a next step, learners should reinforce these concepts through labs, CLI verification exercises, route table interpretation, and packet path walkthroughs. The strongest network engineers are not those who memorize the most acronyms, but those who can explain clearly how traffic moves, why devices behave as they do, and how to verify each stage of the process.